In this short video, we're going to have a look at what entropy is and how it's calculated. In its simplest terms, entropy is a measure of how ordered things are. Now, in the grand scheme of things in the universe, things go from being ordered to being disordered, and things tend to move to being disordered. And there's lots of analogies you can use for this, ideas about, tidying your bedroom, etc. And they're all kind of a bit of an oversimplification. It's more to do with how many different ways there are of arranging the particles. So if something's ordered, you're limiting the number of ways that the different particles can be ordered. And we say that if you get right down onto the molecular level, that the molecules have got a limited number of degrees of freedom. Whereas when you move to disorder, the individual particles have many more degrees of freedom. They've got many more ways that they can be arranged, and this leads to it having higher entropy. So ordered is low entropy, moves to high disorder, which would be high entropy. And the laws of thermodynamics, the second law says that things tend to move from order to disorder. Entropy tends to increase. Now, if entropy is a measure of how ordered things are, it's fairly obvious that the state that something is in, the physical state, is going to have an impact on its entropy. So in a solid, the particles are close together, there's not much movement, there's going to be very low entropy in a solid. Whereas in a gas, you've got much more disorder, many more ways that the particles can be moved around, so it's high entropy. And it would make sense that liquid is somewhere in the middle. Now, if we have a look at the graph showing how entropy changes as the temperature changes and the state changes, there's a few things to notice. So, it goes up and it jumps massively at the points between melting and boiling, because the state change represents a big change in how much disorder there is between those particles. So it increases gradually as you heat up a solid, because as the particles get more energy, they vibrate more about a fixed point, they've got more disorder. But then once it melts and it moves to a liquid, those particles are able to move around more, and so there's a big jump. Now, the jump between a liquid and a gas is even more massive than the jump between a solid and a liquid, and that's because the disorder in a gas and the distances between the particles and the different ways that those particles can be arranged is vastly bigger. There's so many more ways they can be arranged than there is in a liquid, that you get this bigger jump. Another really important thing to notice on the graph relates to the third law of thermodynamics, and that's here. And that's this idea that at zero temperature, and this scale would be in Kelvin, but at zero temperature, so this would be in Kelvin, at zero Kelvin, there would be zero entropy. Now, another thing to think about when saying what factors affect entropy would be whether you've got a pure substance or whether you've got a mixture of substances. Because a pure substance, there's only so many ways you can arrange it, but if you've got a mixture, generally speaking, there are more ways of arranging it. So when you dissolve a salt in water, making that solution involves increasing entropy. So mixtures higher entropy. Now, it's fairly easy to think in terms of low entropy, high entropy. Solids are low entropy, gases are high entropy. But when you actually find out that entropy has numbers on it in the same way as enthalpy does, then that takes a little bit more sort of getting your head around. So we give it the symbol S. So enthalpy is H, entropy is S, and it's got the units joules per mole per Kelvin. You'll notice it's just joules, it's not kilojoules, because we're talking about much smaller amounts of energy than are involved with enthalpy. So enthalpy is always in kilojoules per mole. Entropy is in joules per mole per Kelvin. Okay. And you'll notice that something like diamond, so which is pure carbon, very, very highly arranged, very ordered, has a very, very, very low entropy of 2. Whereas graphite is going to be slightly higher because it's in the layers. There's not as much structure to it, so there's slightly more disorder, slightly fewer bonds between the carbons. So we can see graphite has an entropy of 6, slightly higher than diamonds too. And then as we move into things like water, so water's a liquid, but because it's got hydrogen bonds, it's actually reasonably ordered. The hydrogen bonds mean that the structure of water is quite ordered. So it's still reasonably low at 70, comparable to, say, sodium chloride, which is a solid, which is at 72. And it's only really when we get into things like gases, so water vapour and carbon dioxide, that we start getting into bigger values of entropy. So carbon dioxide is a gas, 240. One of the things you need to be able to do is calculate entropy changes. Now, the formula for this is actually much easier than some of the other stuff we've been looking at recently. So it's delta S, remembering delta is change and S is entropy, and the theta means standard conditions, is equal to sigma, which is in a mathematical Greek letter that means sum of, so the sum of the entropy of the products, and we take away sigma, the sum of the entropy of the reactants. So this is really, really straightforward and something that's very easy to remember. And yeah, so I'll draw a box around it. It's important that you get it down in your notes, but it's going to be quite straightforward and easy to remember. It's just products take away reactants. So let's consider actually working this out. So if we consider the Haber process, we've got nitrogen and we've got hydrogen, and we have 3 moles of hydrogen, and they react together. It's a reversible reaction and form 2 moles of ammonia. Now, just looking at the equation, what would we expect the entropy change to be? If we've got nitrogen's a gas, the 3 moles of hydrogen are a gas, and it's turning into ammonia, but we've got 4 moles of gas on the left-hand side, and we've got 2 moles of gas on the right-hand side. And we've got a mixture of substances on the left, and we've only got 1 pure substance on the right. So I would expect the entropy to go down during this reaction because we're producing fewer moles of gas. So in my little table, we're going to put down what our different entropies of the substances are. So we can see nitrogen gas has an entropy of 192 joules per Kelvin per mole. Hydrogen is 131 and ammonia is 193. So to work out the overall entropy change for this reaction, the entropy of the system, what we're going to do is we're going to add up the entropy of the products. So our 2 moles of ammonia, so 2 lots of 193. And we're going to take away from that our 1 lot of nitrogen, so 192. And our 3 lots of hydrogen, which would be 131. Okay, so if I do 2 lots of 193, that's going to be 386. And if I take away from that the total entropy, the sum of the entropy of the reactants, tap that all into a calculator just quickly. So that's 585. So if I do 386, take away 585, I come out with an entropy change of minus 199 joules per Kelvin per mole. Now, this means that this loses entropy, and that kind of goes against what we've learnt as being the law of thermodynamics, that entropy is likely to increase, things move to higher entropy. But because there's an enthalpy change associated with this reaction as well, and when things get hotter, then the surroundings tend to have their entropy increasing. Then we end up with a balance between the entropy of the system, of the reaction, with the entropy change that's in the surroundings. And this is what drives whether a reaction is feasible or not. And we're going to look at that in tomorrow's lesson on Gibbs free energy, which is where we look at calculating and balancing out the effect of entropy with the effect of enthalpy to work out whether reactions are actually going to go ahead or not. Okay.